As we move into chapter 17, I want to point out that a lot of the material in here is strongly related to the stuff that we talked about way back when in chapter 6, back in Chem 101. So it would definitely be in your best interest to try to review some of your notes from chapter 6 before we move into this chapter. Now, one of the things that we need to describe here is this concept of spontaneity. And we know that, we use the word spontaneous in our everyday language to describe something that somebody does or the way somebody acts that usually doesn't require much planning. In chemistry, the word's used a little bit differently. When we say that something is spontaneous in chemistry, it means that it happens without prodding. Okay, so for example, if I take a glass and I drop it from a great height, when it hits the ground, it's going to shatter. Okay, that is something that will spontaneously happen. I don't have to do anything special to make that work. However, the reverse process of having the glass gather itself back up together again and to reform into a glass, that is not spontaneous. So the process of the glass breaking is spontaneous in the forward direction, but not spontaneous in the reverse direction. And chemical reactions are like this too. Okay, so if we have reactants being converted to products, that process can either be spontaneous or not spontaneous. But if it's spontaneous in the forward direction, then it must be non-spontaneous in the reverse direction. Okay, so one example that we see of this is the combustion of methane. So if we took CH4 and reacted that with oxygen, we would produce carbon dioxide and water. And of course we could balance this. We see here we have one carbon, so we need to put 2 in front of the water and a 2 in front of the oxygen, and we're balanced. Now, looking at this reaction, we know that when we burn something, that process is going to be spontaneous in the forward direction. Okay? But what about the reverse direction? Do we ever see carbon dioxide and water reform into methane and oxygen? Typically, we would say no, because this is an exothermic reaction. So in other words, our reactants are at a higher energy than our products. Okay, so in this reaction, we go from high energy to low energy, so our enthalpy difference, our delta H, is going to be equal to a negative number, which makes sense. When we talk about processes, we expect them to go from high energy to low energy, but that's not always going to be the case. There are many processes that are endothermic, okay, reactions that that actually draw in energy as they proceed towards products. How do we explain that? And honestly, how do we explain the fact that when we take carbon dioxide and water and mix them together, and at very high pressures and temperatures, we do get methane and oxygen? Okay, so apparently there's some kind of a temperature effect here. So what we're going to be doing in this chapter is describing what makes a reaction spontaneous in one direction, but not in another. Okay, so the factor that really decides whether or not a reaction is spontaneous is called entropy. Okay, now entropy is symbolized by capital letter S. Okay, and when we're talking about a change in entropy, we use the delta symbol in front of it. Okay, where entropy itself is a measure, well, I'm going to give you a definition that is not 100% scientifically accurate at first, and I'll try to rationalize it as we move forward in the future videos. But it serves as kind of a measure of disorder. Okay, so like I said, this is an implication of the true definition of entropy, and we'll get more precise as we move along here. But for now, let's just say entropy is a measure of disorder. In the example of the glass breaking, okay, we went from the glass that was all in one shape and one form, okay, everything stuck together in a very organized fashion, and then we dropped it, and all of a sudden it broke up into lots of little pieces that were all over the place. I think that we can all agree that the broken glass is much more disordered than the glass when it was all together. Okay, so when we go from a glass to broken glass, what we're really doing here is going from a highly ordered system, okay, to a highly disordered system. So overall, we're seeing an increase in the entropy for the system, and therefore the change in entropy is going to be positive. Okay, and we could, in principle, attach a number to that, and in fact we will do that a little bit later on down the road here. But for now, let's just recognize that we are going from something that is ordered to disorder, and therefore we are seeing an increase in entropy. Okay, and we'll dig into that a little bit deeper in the next video.